Okay, let's get started by finishing up section 21.2, which deals with alpha halogenation. And we're going to look at this question, 21.12, predict the major product when the following compound is treated with bromine together with sodium hydroxide followed by aqueous acid. So what are we doing? First, we're going to treat this compound with bromine and sodium hydroxide, right? That's going to be our first step. Will be to treat it with bromine and sodium hydroxide. And then in the second step, we're going to treat it with aqueous acid. And this is called the haloform reaction. So this is the haloform reaction. Haloform reaction. And when you do the haloform reaction with bromine, we can in fact call this the bromoform reaction. And I forgot there we go, my subscript 2 for my bromine. Anyhow, I'm not going to draw out the whole mechanism here, but I am going to show you the intermediate that's formed at first, because you know that we have 3 acidic protons here, right? We have 3 acidic protons on this methyl group, and when you pull off a proton with sodium hydroxide and then it reacts with bromine, you end up brominating, and then it renders the next 2 protons even more acidic. Then you brominate again and again until you end up with this intermediate. So let's draw our intermediate, which is going to look like this. We have our aromatic ring. We still have our ketone, but now this carbon has 3 bromines attached to it. And that renders the carbonyl carbon very electrophilic. And so what's going to happen is the hydroxide from sodium hydroxide is going to behave as a nucleophile, and we're going to get a nucleophilic attack here, and we're going to form a tetrahedral intermediate, which is going to look like this. I'm just going to draw pH as an abbreviation for my aromatic ring. I'm going to have the oxygen with a negative charge on it here. I have my carbon with my 3 bromines attached, and then I'll have my hydroxyl. And then I'm going to lose this carbon-based group here. Now, that might not be intuitive, but since we have those 3 electron-withdrawing halogens on that carbon, it can behave as a leaving group, and we're going to end up with this, and it's going to be benzoic acid, right? We're going to end up with benzoic plus the carbanion. Now, the reaction is not done at this point, right? We still haven't treated it with aqueous acid. You might be asking, well, we've got the carboxylic acid. Why would we need to treat it with aqueous acid? The reason why is because the first part of the reaction isn't done, right? I have a strong base, and the pKa of a carboxylic acid, like benzoic acid, its pKa is around 5. And so this is going to behave as a base. Maybe I should draw the bond out here explicitly. Let me draw my oxygen and hydrogen bond like this again. So this is going to behave as a base like this and deprotonate. Then that's going to drive the reaction forward, right, to produce the carboxylate. So I'll just draw it like this. We're going to have our carboxylate, and we're going to have bromoform. Okay, and the pKa of bromoform is around 14. pKa is around 14. And so the equilibrium is going to lie to the side of the carboxylate. And that is why in the last step, you need to treat that with aqueous acid to produce the carboxylic acid. And so what you're doing is you're taking a methyl ketone, okay, this is acetophenone, and you're producing benzoic acid. Very, very important reaction, the haloform reaction. If you do the reaction, the haloform reaction using iodine, okay, if you use I2, it's called the iodoform reaction. And this is actually used as a chemical test to test for a methyl ketone, because when you end up forming iodoform, which is CHI3, it's a yellow precipitate. Okay, that's not covered in our textbook, but when I teach the nursing chemistry lab, we do some chemical tests where we, try to determine is a compound a methyl ketone or not a methyl ketone, and we do the iodoform reaction with them all the time. We don't cover the mechanism, but the students are taught that when they see that yellow precipitate, they know that they have a methyl ketone. So something to think about there. All right, in the interest of time, let's just look at the first problem of 21.13. The first problem, question A, deals with the iodoform reaction. If you've taken a look at it already, which I hope you have, it says identify the reagents that could be used to accomplish each of the following transformations. you will need to use reactions from previous chapters. Well, the first thing that I think about here is in terms of retrosynthesis, right? If I have an ethyl ester, what if I could start with, or what if I could have the carboxylic acid as an intermediate, right? If I could make a carboxylic acid, well, then all I have to do is an esterification reaction where I would treat the carboxylic acid with aqueous acid in ethanol in this case, because I want to form the ethyl ester, and I'm going to have to remove water. So then the question becomes, how would I get from this, alcohol, that functional group, how would I get from there to the carboxylic acid? Well, there's a key step involved here, in my opinion, and that key step is an oxidation. Right? If you're to treat this with PCC, and we were to convert that to a ketone, not only do we have a ketone, we have a methyl ketone. And we just learned that we are able to convert a methyl ketone into a carboxylic acid by first treating it with bromine and sodium hydroxide, then following that up with treatment with aqueous acid. And we would end up with that carboxylic acid that we are looking for, right? And so then the last step is simply going to be the esterification step, okay? So we're going to use our our catalytic amount of acid, ethanol, and the removal of water. And so that problem is really just, 1, 2, 3, 4 steps. Okay, it's a 4-step problem, 4-step synthesis. And 2 of the steps go together in the haloform reaction. Right, so what's the problem here, really? Why is this a difficult problem? Why is this in chapter 21? Because it's not as abundantly clear as some of the syntheses that we looked at earlier on in this class, how to take, this compound and get, how to go from this secondary alcohol to this ethyl ester. Okay, so this is why you have to have reactions like the haloform reaction down pat. Okay, so that you're able to confidently do a quick retrosynthesis and be able to start moving forward from there. All right, well, let's move on to section 21.3. This is a really important section. It deals with a type of reaction that we call an Aldol addition reaction. Recall that when an aldehyde is treated with hydroxide or an alkoxide, you have an equilibrium where you have significant amounts of both the aldehyde and the enolate, right? If we were to take this aldehyde here, this is acetaldehyde, and we were to treat this with sodium hydroxide, not only do we have the aldehyde, but we'd also have some of the enolate, right? We talked about that at the beginning of the beginning of this chapter. We said, okay, well, if you only want to do partial deprotonation, you would treat your aldehyde with sodium hydroxide. So in fact, you have both of these in the reaction mixture. Right now, we're just taking that for granted. We know that because we've studied organic chemistry enough to know that when we treat this aldehyde with sodium hydroxide, we're going to have both of those in solution. So what does that mean? That means that the enolate can behave as a nucleophile and it can attack the acetaldehyde, which will be an electrophile, like that. And we call that an Aldol addition reaction. Why? Because we end up with a compound that has both an aldehyde in it and an alcohol in it. So that's where we get that's where we get the name aldol. Note the location of the hydroxyl. It's on the beta carbon. So we call this a beta hydroxyaldehyde. And I might refer to that throughout the lecture. Anyhow, I've drawn the first 2 steps, or I've drawn a couple of steps here, really. I've drawn the nucleophilic attack of the enolate. But let's take a look at the mechanism in greater detail. The first step is actually the deprotonation of the aldehyde, isn't it, right? We know that we have 3 acidic protons here, 1, 2, and there's 3. We leave those 2 out. We only show one of them for instructional purposes. The first step is going to be the proton transfer, which is the deprotonation to form the enolate. Here's your enolate. Again, you're only going to deprotonate some of the aldehyde molecules. Okay, some of the acetaldehyde will be deprotonated, and so it's going to behave as a nucleophile, and it's going to attack some of the other molecules. Then we end up with this alkoxide, and that resulting alkoxide ends up being protonated to produce the beta hydroxyaldehyde. Remember, this is the alpha carbon, this is the beta carbon, so that's why we call it a beta hydroxyaldehyde. So that's an aldol addition reaction. You end up with an aldol, a compound that has both an aldehyde and an alcohol functionality into it. I just want to back up for a second here and point out one important thing that's going to come up later on in the lecture, probably in just a few minutes, is that when the aldol addition reaction occurs, no heat is added, because we're going to see that if we heat up this reaction mixture, if we take these conditions and we add heat to them, we're going to end up with something that's a little bit different. So you could even write here, I mean, you're not going to have to write this as a reactant, no heat, but there's no heat used in an aldol addition reaction. Now, what about these aldol additions? Do they work for all aldehydes? Well, for simple aldehydes, like this is butyraldehyde here, or butanal, you can see that when you treat that with sodium hydroxide and water, no heat, we end up with the aldol product, the beta hydroxyaldehyde, in a 75% yield. It's a pretty good yield. But if you use something like cyclohexanone, wow, in that case, you don't end up with a very good yield at all, okay? It's an equilibrium, right? And the product simply is not favored. And so you end up with a really low yield reaction, not a very useful reaction. And in fact, we can draw a mechanism for the reverse process, right? We know that from here and here, we know that these processes are in equilibrium. And if you're wondering, what would the mechanism be in the reverse? Well, based on the principle of microscopic reversibility, the mechanism going backwards, which is called a retroaldol reaction, is identical to the aldol formation. It's just drawn in reverse, and here it is, okay? So if you understand how to draw the forward process, the aldol addition mechanism, you, my friend, can draw the retroaldol reaction. The first step is a proton transfer, right? Remember that during the aldol addition, the last step was a proton transfer. So again, our first step is the proton transfer, the deprotonation of the hydroxyl to produce this alkoxide here. And then we end up breaking it apart, right? And we expel the enolate as a leaving group. And then the enolate can, of course, be protonated. So that's the retroaldol reaction, okay? And again, as long as you know the mechanism for the aldol addition, you'll be able to draw the mechanism for the retroaldol. By the way, just as an aside, all of these mechanisms are important, okay? If there's any mechanism that is not important in this chapter, I will tell you. So every mechanism that we've looked at so far is a very important mechanism, and a mechanism you should understand and be able to draw. Okay, well, what happens if we were to add heat to these reaction conditions? Okay, you even see it down here. I have sodium hydroxide, water, and heat added. Well, when we heat up our reaction mixture, the same kind of conditions that we were using for an aldol addition, we get what's called an aldol condensation. So follow along with me. When an aldol product is heated under acidic or basic conditions, an alpha-beta unsaturated carbonyl forms. So we can end up with an alpha-beta unsaturated aldehyde or an alpha-beta unsaturated ketone. We call this aldol condensation. Why do we call it a condensation? Well, it's because we lose water, right? You think about condensation on a coffee table on a hot day. Well, what's condensing on the sides? It's water, okay? We use condensation as a general term in organic chemistry to mean the loss of a small molecule. It could be nitrogen, it could be carbon dioxide, but in this case, it is in fact water. So what am I getting at? Is if you take your aldol product, okay, and you heat that up in the presence of acid or in the presence of base, you end up losing water. You lose a proton from the alpha carbon and the hydroxyl from the beta carbon, and you end up forming a double bond. And we call that the aldol condensation product, the alpha-beta unsaturated aldehyde in this case. Okay, so again, we can form an alpha-beta unsaturated aldehyde if we're starting with an aldehyde, and an alpha-beta unsaturated ketone if we're starting with a ketone. Again, by now, I hope you have this down pat, but the carbon after the carbonyl is the alpha carbon, and this is the beta carbon, so that's why we call it alpha-beta unsaturated. Aldol condensation, again, occurs when the aldol addition is performed at elevated temperatures. And so the only thing that we're changing from the reaction conditions for an aldol addition is we're adding heat. That's all. Okay, you remember the conditions for aldol addition were just sodium hydroxide and water. Okay, the reaction conditions for aldol condensation are sodium hydroxide, water, and cooking it up, right? Heating to drive off water. Again, aldol condensation occurs when an aldol addition is performed at elevated temperatures. This slide is a really great summary of what we've just learned. Okay, so for the aldol addition, I'll remind you again, let me get at my blue pen, that the conditions would be sodium hydroxide in water. And then for the condensation, it's going to be sodium hydroxide, water, and you're going to heat that up. All right, to produce an alpha beta unsaturated aldehyde. And of course, you lose water because it's a condensation reaction. There we go, a really great summary. Now, you might notice that the conditions for aldol condensation are only a little bit more vigorous than the conditions for aldol addition. So the driving force of the aldol condensation reaction is in fact the formation of a conjugated system, right? It goes double bond, single bond, double bond. And that is what pushes the reaction equilibrium forward. That's the driving force of the reaction, the formation of that conjugated system. Well, let's talk about the mechanism of aldol condensation. And we've already looked at the mechanism for the formation of the aldol product. And so when we move to the next slide, what you'll notice is that the aldol condensation mechanism, part one, is something you've already learned, right? We just talked about this. The proton transfer to form the enolate, then the enolate serves as a nucleophile, attacks the aldehyde. Then we have a proton transfer, right? This has already been covered. The next step, though, is the elimination of water from our aldol. And the way that that works is first hydroxide comes in, behaves as a base, and it's going to deprotonate at this position. Why? Because that proton that I have circled in blue is relatively acidic because it's alpha to a carbonyl, right? We could draw a resonance stabilizer or another resonance contributor here where we have the negative charge on the oxygen. I'm not going to do that now, but then we end up losing hydroxide as a leaving group. Now, you might be thinking, well, hold on. I don't really think of hydroxide as being a good leaving group. And in most cases, it isn't. But this is a special mechanism. We call this an E1CB mechanism, right? E1, just like an E1 that we learned way back in chapter 7. But this is an E1CB, and the CB stands for conjugate base, okay? An E1 conjugate base reaction. That's the C and the B, okay? E1 because it's one at a time, right? It's a two-step process. The first step is the deprotonation, and then the loss of the leaving group, the hydroxide. Again, you might not think of hydroxide as being a great leaving group, but remember, the driving force of this reaction and the reason why hydroxide can be a good leaving group is because we form that conjugated system. Now, another thing that you might be asking about or might be pondering is saying, well, come on, I have a sigma bond here that has free rotation right here, okay, and here as well. Why did you draw, the trans product or the E product here? Well, when it comes to stereochemistry, when you can form two stereoisomers, the major product is going to be the one with the fewer steric interactions, nothing more than that, okay? So when we draw the product of our aldol condensation, the major product is always going to be whichever one, whether it's E or Z, cis or trans, depending on the situation, whichever one just has the least steric hindrance, that's going to be your major product. In fact, if you rifle through the problems that I assigned from this chapter, or the problems that I pointed out, or the problems I asked you to do anyhow, I don't even know if he asks you to, designate major and minor products, really. There might be one in there, but I don't remember it. Anyhow, a little bit more about that driving force. Okay, I've told you that the driving force for an aldol condensation was the formation of a conjugated system, right? The alpha beta unsaturated aldehyde or a ketone. Well, this is a very specific example, right? What's this ketone that we're starting with over here, right? That's acetophenone. Now, if we take acetophenone and we treat it with the same old conditions that we did for the aldol addition, just some sodium hydroxide, you notice that there's no heat here. You can't even get the aldol product, okay? So this is the product from the aldol product, or aldol addition product, okay? Aldol addition product, okay? You don't even get that product at all. You only get the product from the condensation. Can anybody give me just a guess, and it's the simplest possible answer as to why you only get the product of aldol condensation. There must be a driving force. Yeah, Sean said stability. Absolutely. It's because it's so highly conjugated. Only product form because highly conjugated. Okay? This is just a specific example, okay? And it's not about you having to memorize, a million different specific examples. It's about you understanding the idea is that the more conjugation you have, the more difficult it would be to isolate the aldol product, okay? You can see everything is fully conjugated, right? Double, single, and then we get back into another aromatic ring. So completely conjugated system, all right? Can't even isolate the Aldol addition product if that's what you want. Can't get it. Okay. The yields for condensation are generally speaking much higher than the yields of addition. Okay, and again, the driving force is the formation of the conjugated system. The reason that this reaction occurs in such a poor yield, the reason we get such poor yield for the aldol addition is because the reaction is in equilibrium and the aldol addition product simply is not favored. That's it. Okay, nothing more than that. So again, aldol condensation may be a more useful reaction, generally speaking, because we get greater yields. And organic chemists are always looking for a good reaction that is high yielding. Something I haven't mentioned this morning, and I don't know if I mentioned it in the last, well, no, I wouldn't have mentioned it in the last class, but something about these aldol reactions that you may have noticed is that you're forming carbon-carbon bonds, right? You're forming a bond between this carbon and this carbon, right? And as I told you in organic chemistry, whenever you can form carbon-carbon bonds, you can always gain some kind of notoriety. Now, the aldol condensation and aldol addition are not named after anybody per se, but these are very powerful reactions. Still very, not still, they're just widely used, in organic chemistry. Very important reaction. Well, let's talk about, some complexities of aldol reactions. So far, all the examples that we looked at, we had one type of aldehyde, right? Now, what if you had two different aldehydes? Here we have two different aldehydes, right? It's a kind of a small print here, but here we have acetaldehyde, that's the common name of that aldehyde. The systematic name would be ethanal. The systematic name of this aldehyde would be propanal. Its common name is propionaldehyde. I asked you to memorize that back in chapter 19, the aldehydes and ketones chapter. Well, what if we took those two aldehydes and we mixed them together with some sodium hydroxide? Not only are we going to have both of those aldehydes in solution, we're going to have both of their enolates. We're going to have the acetaldehyde enolate, and we're going to have the enolate of propionaldehyde. And so we're going to have four different species in solution. And if we have four different species in solution, we can end up making four different products. Look, if I have two molecules of acetaldehyde reacting together, two molecules of propionaldehyde reacting together, I can get two different products. And if I have the enolate of the propionaldehyde reacting with acetaldehyde, that gives me another product. And if I have the enolate of acetaldehyde reacting with propionaldehyde, that gives me another product. Now, I'll be the first person to admit that it's not very useful to mix acetaldehyde and propionaldehyde with some sodium hydroxide. That doesn't sound very fun to me at all, because separating four different compounds is pretty difficult, right? Some of you did a reaction yesterday in the lab and looked at a TLC. And in some of those spots, you might have had, the major product and then maybe a little bit of a side product. And it makes it more difficult to interpret. I can tell you that to purify it is even more difficult. Okay, and so this doesn't sound like it's a very useful reaction to me, but there are ways that we can get around that. Okay, a couple of ways that we can get around that. And when we do these crossed aldol reactions, so using two different carbonyl compounds, they're only practical when the number of products can be minimized. And we've got a couple of ways that we can do that. Okay, the first one is if one of the substrates is relatively unhindered and doesn't have alpha protons. Let me explain this one to you. Here we're taking formaldehyde. It's got no alpha protons, so that means it can't be deprotonated. Right? You cannot form an enolate of this compound. Impossible. You can form an enolate of propionaldehyde. Of course you can, because it's got 2 alpha protons, right? This is the alpha carbon. It's got 2 alpha protons. Now you might be saying, well, come on. If I was to treat this in sodium hydroxide, come on, Mr. Dion, I'd still get 2 products, because I'd have the aldehyde and I'd also have its enolate, right? You'd also have this. Well, the answer is it depends on the situation, okay? There probably are scenarios where this would give you a mixture, but this specific scenario, and if you're like, oh man, another specific scenario, what he's getting at is this. If you have something like formaldehyde, which is just so tiny, it is so much more reactive than propionaldehyde that your enolate is only going to attack, it's only going to end up attacking the formaldehyde, okay? Because it's just going to react faster. Nothing more than that. It's just more reactive. Okay, so that's one way that you can get around it. As I said, there's a couple of ways to get around it. So what's the second way? This is just more information on the first one. Here's a specific example. If you take benzaldehyde, this is benzaldehyde right here. If we take benzaldehyde, the same thing applies here. It's got no alpha protons, and so the propionaldehyde is going to attack the benzaldehyde. It says this is possible when only one compound can form an enolate and the other compound reacts with the enolate faster. So here's another like very specific example. We take propionaldehyde. It's the only one that has alpha protons, right? It's got 2 alpha protons. You form the enolate and it reacts with benzaldehyde faster than it would react with another molecule of propionaldehyde. Another driving force here is that you end up forming this highly conjugated compound, right? If this reacted with a molecule of the enolate, okay, you're not going to get a highly conjugated system. Okay, so that's enough about that. Let's move on to the second way that we can guide our reaction or make the aldol condensation or the aldol addition or aldol condensation more practical, and that's to use LDA as a base. Right? Remember we talked about LDA earlier on? It was lithium diisopropyl amide. So LDA is this guy. So we have a nitrogen with 2 isopropyl groups on it like that. It's also got 2 lone pairs. So the nitrogen has a negative charge like that. And then lithium is the cation. You probably remember that I showed you how to make that during the last lecture from diisopropylamine and N-butyllithium. Okay, when we take a ketone, here they're showing acetone, okay? When we take a carbonyl compound like acetone and we treat it with LDA, LDA is a really strong base, and so we get total and complete deprotonation. We discussed that in the last class. Now I've got this enolate, okay? So what you literally do, and you're going to have to forgive me here, I'm going to try my best, okay? You literally added LDA to a solution of the ketone, to the acetone. So in solution, you have this, okay? And it would have a lithium cation like that. Anyhow, you have this. So then what you do is called a directed aldol addition. So one compound is completely converted to the enolate. So here's my enolate right here in my flask. The other carbonyl compound is slowly added. So then what you're going to do is you're going to make a solution of this compound, and you're going to add it in here dropwise. So you would literally take a pipette, okay? In fact, you would probably use a needle, but you would take a pipette and you would drop this compound in here, bloop, 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 right? The propionaldehyde, okay? And what's that going to do? As soon as the molecule of propionaldehyde is exposed to this enolate, the enolate is going to attack it immediately, right? It's going to, boom. That wasn't a very good arrow, was it, right? It's going to, pow, attack it like this to produce this intermediate. Okay, now the success of this directed aldol addition, and I worked with a couple of guys who are experts in directed aldol addition, the success is going to be limited by the rate at which the enolate can deprotonate the electrophile. And if you're like, what do you mean by that, Mr. Dion? Well, if you think about it, the enolate can also behave as a base. right? Now this is mentioned in our book. He mentions it very quickly, but I just want to throw it out there for anybody who's got a really inquiring mind, right? Because we know there's two alpha protons here, right? So if you're thinking, what's to stop the enolate from just behaving as a base, right? Why is it acting as a nucleophile? Well, the answer is it could probably do both. And the success of the reaction will depend. Okay, it's going to depend on, the rate at which the enolate can deprotonate the electrophile compared to the rate of the nucleophilic attack. Now, if you're wondering, okay, well, how are you going to control that? What are you going to do? Well, the answer is it's probably substrate specific, right? Depending on the reaction or the molecules, you might adjust the temperature or maybe solvent or something like that. Okay, but for our class, you can assume that when you treat when you do a directed aldol addition, that you're only going to get nucleophilic attack of the enolate. Okay, and I probably spent too much time talking about the competition here, but again, in case somebody's really wondering, that is the answer. Now, what if we have two ketone functionalities in the same molecule? What if I was to treat this molecule that I have here, right? This is let's count the carbons. We have 1, 2, 3, 4. So this is a 1,4 diketone, right? The molecule is what? 2,4 hexane dione would be the name of the molecule, okay? But it's a 1,4 dicarbonyl, okay? So if I have a 1,4 dicarbonyl, what if I was to treat that with sodium hydroxide, right? I've got all kinds of acidic protons all over the place, but you can imagine that I could pull off one of these protons right here. I'll just leave in one. What the heck? I'll draw all three. It's Friday. Okay. If my hydroxide behaves as a base, okay, it can pull off one of those acidic protons like this. And then I would end up with an intermediate that looks like this. So I'd have this intermediate. Okay. Now I've got a nucleophile, right? Here's a nucleophile, and I've got an electrophilic carbon all in the same place, right? And that's what's drawn right here, okay? You just kind of curved it around so you can see how the ring is formed. So what's going to happen here is we're going to get an alpha, beta, unsaturated ketone in this case. Now you might be wondering, okay, well, aren't there acidic protons here, Mr. Dion? Like, aren't these two protons acidic? Why wouldn't I rip off one of those protons and get a nucleophilic attack like that? Well, it's covered in the book. I don't have it in my slides, but it shows it in the book. And the reason why those green protons wouldn't be removed, or why they wouldn't be preferably removed, is because in that case, you'd end up with a 3-membered ring, which would be really strained because you'd have a 3-membered ring with a double bond in it. So the conclusion is that only 5- and 6-membered rings are formed well this way in an intramolecular aldol reaction. So we have our nucleophilic site, we have our electrophilic site. They're drawn right here, and I'll redraw them over here, is that you're going to have this acting as a nucleophile and this carbon acting as an electrophile like that. Okay, so that's an intramolecular aldol reaction. Kind of a neat reaction. We don't look at an abundant in this class, but we will look at another one before the chapter is over. Okay, well, that's enough of me yakking. Let's try a problem. What time is it? 8:36. All right, let's try a little problem here. This is question 21.14. It says predict the major product obtained when each of the following aldehydes is treated with aqueous sodium hydroxide. Note that it doesn't mention anything about heat, okay? So no heat. Therefore, this must be aldol addition. So the products, you can see that we're starting with two aldehydes. The products are going to be beta hydroxy aldehydes in this case. All right. Well, there's a really handy skill builder that you can use to help you learn to identify the products of aldol addition and aldol condensation. I don't bring up the skill builders a lot in this class, but I'll tell you that this one is a great one. It's skill builder 21.3. It's more geared towards aldol condensation, but I promise that it will help you with aldol addition reactions. Now, in the interest of space, let's just draw an acidic proton here. Of course, there's a second one. I'm just going to, well, maybe I'll draw the second one. I say that every time, don't I? Okay, I'm going to treat this with sodium hydroxide, right? NaOH. My my hydroxide is going to behave as a base, isn't it? It's going to deprotonate, right there, and I'm going to end up with this compound. So draw my aromatic ring. And then I have 1, 2. I'm going to have a negative charge here, and I'm going to have this. But remember, I'm not only going to have this compound in solution because I'm treating it with sodium hydroxide. Therefore, I'm only going to get partial deprotonation, not complete deprotonation. And so in the interest of space, let me move this stuff up here. Oops. Oh, go. That. Okay, just in the interest of space, I'm going to delete this, what I've drawn over here, because we're going to have in solution, we're going to have this intermediate, right? We're going to have this guy, this enolate, and we're also going to have this aldehyde, right? Both of them are going to be in solution. We treated it with sodium hydroxide, not LDA. If we treated it with LDA, we would only have the enolate, but now we've got both. And so we've got a nucleophile, the enolate, and we have an electrophile, the aldehyde. And so we're going to get a nucleophilic attack like this. Again, in the interest of space, I'm just going to draw it like this. And then what are we going to end up with? Well, after a proton transfer, we're going to end up with something, and there's a variety of ways that you can draw it, okay? Why don't I just try to draw it in the orientation that it is here? So you're going to have your aromatic ring, and that's this aromatic ring right here. So you have 1, 2, 3, fix that, 1, 2, 3, like that. There's your aldehyde. Okay, what's going to be attached to this carbon? Okay, you're going to have a carbon attached to it. This carbon is this one right here. What's going to be attached to that carbon? It's going to have the hydroxyl after it's protonated. It's also going to have this proton. I'm not going to draw it in. Then you have 1, 2 carbons, 1, 2 carbons like that, and then you're going to have your aromatic ring. Okay, now if you're like, oh man, how would I put all this spinach together? Well, you're going to have to practice it. Okay, I promise you that everybody is going to have to practice it. Don't think, oh, it's just me that has to practice this. No, that's why I mentioned the skill builder too. It really takes a keen eye, or a strong sense of mechanisms to be able to draw the products, quickly and effectively. Let's try the same thing down here with the second one. Okay, I'm starting with cyclohexane carbaldehyde. I treat that with sodium hydroxide. Let me ask you guys a question. How many acidic protons are there in cyclohexane carbaldehyde? And it's not a trick. Mr. Dion doth not like tricks. How many acidic protons are there here in cyclohexane carbaldehyde? Yeah, both students who answered are both correct. There's only one, right? There's just this guy here. That's it. So that means we would produce this enolate as an intermediate, where there's my aldehyde, and my negative charge is going to be here. Okay, I'm just putting these in brackets just to say, well, it's an intermediate. Okay, it's not a final product or anything. And now we've got a nucleophile and we've got an electrophile in the same reaction mixture. Now, again, I'm not drawing all the mechanistic steps, so that's why we put more than one arrow, just to mean like there's more steps that follow. But let's see if we can draw the final product. We'll start by drawing the cyclohexane carbaldehyde. And what's going to be attached to this carbon? Well, it's going to have a hydroxyl attached to it, like this. You can see it's not super pretty the way that I'm drawing it. And it's also going to have a 6-membered ring attached to it. Come on, there we go. All right, it's going to look something like that. Now, there's much prettier ways to draw it than this, but I'm trying to just show you the connection, with just making it easy and starting over with the aldehyde like that. Okay, give me a thumbs up if you think you could do that with a little bit of practice. Trust me, it takes some practice for everybody. All right, wonderful. Yeah, Mauricio, I agree with you, man. I agree with you 100%. You know what, Mauricio? Again, I'm going to refer to this skill builder again. You want me to show you the way the skill builder does it? I can show you. So again, skill builder, what was it, 21.3. Let me show you the way that the skill builder works, okay? Draw the condensation products from aldol condensation when each of the following compounds is heated in the presence of aqueous sodium hydroxide. Okay, I'm going to teach you the skill builder way, okay? I'm a kind of guy that likes to draw mechanisms and all that kind of stuff, but look, I've taught organic chemistry long enough. I'm not a fool, okay? I know that my students like, the skill builder sometimes. Okay, so here's what you do. Watch carefully. You start by, I'm going to redraw the starting material like this, okay? Draw the 5-membered ring like that. Okay, now I'm going to copy and paste it. So I'm going to draw it twice. So I'm going to take it and I'm going to copy and paste. Okay. Now hold on a second. I can't do this without drawing reaction conditions. I'll put sodium hydroxide, water, and heat, and not H2O, heat. So let me just move things around here. Okay, fix this. Move it over here. Okay, so here's what you do. You start by redrawing the aldehyde like that. You draw in the 2 acidic protons, right? You've got to have at least 2 acidic protons. So let's draw them in explicitly. Here's 1 acidic proton. Here's the other acidic proton. If you want to, on the oxygen of the other aldehyde, you can color it in red if that helps you, if color coding helps. And then what you're going to do is you're going to orient these in such a way that the 2 acidic protons are right next to that oxygen of the carbonyl. Okay, so those 2 are going to be right next to each other like that. And that is where you get the H2O from. It comes from here, H2O. Okay? And so when you draw the product, you redraw your starting aldehyde like that, 5-membered ring. Okay? Where all this spinach is, you put a double bond, and that's it. You draw the rest of the aldehyde. I'll just kind of put it off to the side like this, just in the interest of room. And there you go. That's the product of the aldol condensation. Look, you get an alpha beta unsaturated aldehyde. Does that help using the skill builder method? Again, I highly recommend, looking at the mechanism in detail. But if the skill builder method helps you, I don't have a problem with that. Well, with that in mind, let's try the next one then. The next one, we'll do this exact same technique. I'll do it a little bit faster. So let me divide the space here. Explore the space, Gene. Okay, so if we draw the ketone, so this is what? 4-heptanone. So let's draw 4-heptanone. 1, 2, 3, 4, 5, 6, 7. I'll draw it carefully like this. I'm going to copy it. So copy, and I'm going to paste it right here like this. Okay. So what I'm going to do is I'm going to draw in my 2 acidic protons right here. Where's my pen? Here we go. 2 acidic protons like that. Here's the oxygen. That's where I'm getting my H2O from, right there. And so what you end up with as a product is this. You have 1, 2, 3, 4, 5, 6, 7. Double bond here. And then you just draw the rest of the other compound. There you have it. And you can see again that you have an alpha beta unsaturated ketone in this case. And so that's the product of the aldol condensation. After you treat that ketone with sodium hydroxide, which is aqueous, of course, and you heat it up. Again, the way that I, recommend, trying to figure these out is skill builder 21.3. Maybe you could use the skill builder kind of like training wheels, and then once you've mastered it, you can, take the training wheels off. Okay, there we go. Let's try another one where we have to identify the reagents that can be used to produce each of the following compounds via an aldol reaction. The first one, B, is the product of an aldol addition, isn't it? Because we have a beta hydroxy ketone, right? We don't have unsaturation, or sorry, we don't have a double bond in there. So this is the product of aldol addition. So that means the conditions are going to be just sodium hydroxide and water. Well, the best way to figure out what the reactants would be are to draw the lone pairs in on the oxygen of the hydroxyl like that. And then what I like to do is I say, well, if this is my alpha and this is my beta, that's the bond you're going to break, okay? That's the bond you're going to break in your retrosynthesis. You can either draw a line through it like this, you know, that works, but I think an even better way to do it is to draw some curved arrows and say, well, I'm going to reform a pi bond like this, okay? And I'm going to put my pair of electrons over here. And so that's a retrosynthesis. And what would you end up with? If you did that retrosynthesis, you would end up with this enolate, right? You'd get that enolate. And then you'd also end up with something that looks like this, where you have a double bond to your oxygen. I'm going to eliminate the hydrogen. I'm going to draw a tautomer of it, okay? Or I guess it's not completely a tautomer, but yeah, anyway. What you would end up with is something like this, right? So that tells you what the starting materials are going to have to be. You're going to have to start with this aldehyde, and you're going to have to start with this ketone. And so if I just move this over here a little bit in the interest of space, okay, let me move this over here like this. What would you use? You know, first you would take cyclohexanone, right? You'd take cyclohexanone and you would treat it with sodium hydroxide and water, NaOH and H2O. And what's the electrophile that you would put in? You would put in that aldehyde that I drew here. It's just 1-methyl cyclohexane carbaldehyde, right? And there you go. And that would give you the final product. Let's try the next one. The next one's a little bit different, isn't it? Because it's an alpha beta unsaturated ketone. Again, here's our alpha and our beta. So this is an aldol condensation. So that means we're going to need sodium hydroxide, water, and we're going to have to heat this up. The same thing applies here. We're going to do a retrosynthesis, but think back to the way that I taught you with Skill Builder 21.3, right? We're going to break this double bond right here, and then retrosynthetically, we're going to be able to draw the two reactants. We're going to need this aldehyde. So we have this, and we have our double bond to our oxygen like this. So that's one of the reactants that we'll need. And then we're also going to need this guy with the two, right, with two acidic protons, right? So you need cyclopentanone and benzaldehyde. Those are the two compounds that you're going to need to do this reaction. So how would I write that out? Well, I mean, I would accept more than one way of writing it out. Again, there's my retrosynthetic analysis. So the way that I would write this out is I would say you take cyclopentanone, you combine it with benzaldehyde, like that. You treat it with sodium hydroxide, water, and you heat it up. And that's going to give you the product. Okay? Again, I'll point out that earlier on, we looked at a specific example with benzaldehyde, and we said, well, benzaldehyde reacts, you know, so quickly it doesn't have any alpha protons, and so that's why the enolate is going to preferentially attack the benzaldehyde instead of reacting with another molecule of cyclopentanone. Okay, there you go. Some intramolecular, or these are intermolecular aldol reactions, aren't they? That's not a very good title for the slide. Anyhow, the next problem deals with intramolecular reactions. Is draw the mechanism for the following transformation. Well, we can see that we're forming a 5-membered ring here, and this is a reaction that we looked at earlier today. So I'll go over this kind of quickly. the first thing we're going to do is we're going to rip off this proton. The reason we're not going to rip off, and you probably do rip these protons off, the green ones, is because that would result in a 3-membered ring, which is more strain. And so the equilibrium is going to push for deprotonation of the red proton, because in that case, you end up with the desired 5-membered ring, which is preferential. So hydroxide is going to behave as a base. It's going to strip off this proton, right, like that. We end up with our enolate. Let's draw the enolate. 2, 3, 4, 5, 6, like that. There we go. So now we've got a nucleophile and an electrophile all in the same molecule. Now you remember how he drew it, he drew it like this, and then he had the negative charge like this, and he kind of set it all up so that you could see how you would form a 1, 2, 3, 4, 5-membered ring after the nucleophilic attack. Well, to heck with that. Let's do it the hard way. Okay. Let's just draw it straight and let's just count some carbons and we'll be able to get the right answer, I promise. So we're going to get a nucleophilic attack like this. Then you can just kind of tally them up. Look, I've got 1, 2, 3, 4, 5 carbons in a ring. So what's that going to look like? Well, it's going to look something like this: 1, 2, 3, 4, 5, right? And if I number these, okay, if I number this, 1, 2, 3, 4, 5, like that, on carbon number 2, I'm going to have my carbonyl. And on the 5th carbon, I'm going to have this oxide and a methyl group, like that, right? Well, remember that in the first step, when we did the deprotonation, what did we form? We formed water, right? So now there's water in our reaction mixture, and so the water is going to behave as an acid, and we are going to protonate, right? We're going to end up protonating that oxide, and so the alkoxide. So we end up doing something like this. Okay, so let's draw that intermediate. So here's our aldol, which we are not isolating. And let me label it for you. So this is the aldol. Okay, again, we're not isolating that. And next we're going to eliminate the hydroxide. And again, I mentioned this to you earlier, and I said, you might not think of hydroxide as being a good leaving group in organic chemistry, and it isn't, but this is an E1CB mechanism or an E1CB reaction, an E1 conjugate base mechanism, where first we form the conjugate base. So let's draw the conjugate base out like this. So we have our negative charge like that. We have our, right? And then we end up losing the hydroxide as the leaving group in this E1CB mechanism, right? And what's the driving force for that? It's the formation of the conjugated system. Sorry, I'm trying to get my negative charge a little prettier there. Okay, so we expel hydroxide as the leaving group like that. And there we go. We end up with our product like that. Okay, again, intermediate has to be an aldol, and then via the E1CB reaction, we end up losing hydroxide. Okay, let's switch gears again and get into section 20.4, which deals with Claisen condensation. So the Claisen condensation. So far, we've looked at enolates formed from aldehydes and ketones. Oops. And now we're going to look at the same sort of reaction, but using esters instead. Okay, so we're going to do condensation reactions with esters, and we have a name for those. They're named after a scientist named Claisen, so the Claisen condensation. What we do is we start out with an ester. We treat that with an alkoxide, and I'll talk about that more later, which alkoxide, because, a question you guys love to ask me sometimes is, why is it ethoxide sometimes? Why is it methoxide other times? Well, here's an example of the alkoxide that you choose actually being important, and I'll get into that more later on. But we do a deprotonation to form an enolate, and then that enolate can do a nucleophilic acyl substitution on the other another molecule of the ester. and we end up with a beta keto ester. So beta keto esters. And I took advanced organic chemistry. I did a whole chapter on beta keto esters. All right, so let's take a look at the mechanism, and I bet you could already draw it, you know, just based off of your previous knowledge of organic chemistry. The first step is going to be deprotonation, the proton transfer, and we form an enolate, right? Here's the enolate, and that enolate is, we're only going to get some of the enolate, right? Because sodium hydroxide is not a strong enough base to completely deprotonate everything. And so we have the enolate act as a nucleophile, and another molecule of the ester is going to undergo nucleophilic attack to produce a tetrahedral intermediate. We have our loss of a leaving group, but the leaving group that's lost is an alkoxide, and so we're not done at this point. The reason why we have to have two steps in this reaction, the reason why we have to first treat it with sodium methoxide and then with aqueous acid is because the alkoxide actually deprotonates this 1,3-dicarbonyl to form a doubly resonance stabilized enolate. That's this guy right here. You could put the negative charge up here or up here in two different resonance structures. And that is, in fact, the driving force of the reaction. That's what drives the reaction to completion, is this step right here to form this intermediate. And that is why we need a second step, right? The treatment with aqueous acid in order to protonate. And so the first step in this case would be we'll put here sodium OR, because they're not specifying what the alkoxy group is. And then the second step would be to treat that with aqueous acid, like that. Okay, those are the two steps that are required for the Claisen condensation. There are some limitations to the Claisen condensation, just like there were in aldol chemistry. The first limitation is that the starting ester's got to have 2 alpha protons. Why? Because removal of the second proton is what drives the equilibrium forward. Let me back up and show you in case you're not following me 100%. Right? The first proton in this case was lost right here. But we ended up losing a second proton in this step. And if you don't have at least 2 protons, you've got to have, this is the second proton removed, right? Second proton. Without a second proton, you can't form this intermediate, which is the driving force for the reaction. So that's the first limitation. And the second one is you can't use hydroxide as your base. And you might be thinking, well, come on, if I evaluate the pKa's, hydroxide should, you know, be in equilibrium. But the problem is, hydroxide can't be used as a base. Why? Because you're going to end up doing a basic hydrolysis of an ester and end up with a carboxylate, and that's just going to destroy your starting material. Now, it says here, basic ester hydrolysis occurs. That has a name. It's saponification. Saponification. Okay, so that's what's going to happen if you were to try to do a Claisen condensation with hydroxide. So again, the choice of the alkoxide is important, and it can't be hydroxide. This is what I was getting at earlier on. You guys love to ask me, you know, why do you use methoxide? Why do you use ethoxide in certain cases? Well, sometimes it doesn't matter. And in fact, every time that we've looked at an elimination, when we learned, you know, E2 reactions back in the day in chapter 7, in those cases, I always told you, it doesn't matter. You can choose whatever you want. The pKa's are going to work everything out, whether you use methoxide or ethoxide. Here's a situation where the alkoxide does matter. You choose the alkoxide that matches the OR group. Okay, it's got to match the OR group. Here's our OR group. Since it's O-ethyl, since it's OET, okay, over here, you would not want to use methoxide. You would actually want to use ethoxide. Okay, in this case, you'd want to use OET minus. Okay, and the reason why is because the methoxide can come in and act as a nucleophile, and you end up doing what's called a transesterification. It's a big word, you know, big fancy word, but all it means is that you're going to swap out the ethoxide for a methoxide. Now that's not very useful, is it? Right? If we go all the way back here in this example, you see the first thing that we showed you was that you have the OR group as being an O-ethyl, and we used ethoxide. If the scientist had chosen sodium methoxide, okay, if the scientist had, you know, messed up and chose sodium methoxide, they would get this product, but they'd also end up with the transesterified product. They'd also end up with the methyl ester. So then you get a mixture, right? That's not very useful, is it? Because those two compounds are so close in terms of their polarity that trying to separate them is going to be very difficult. So you really just end up in a mess, okay? So again, it's a situation where the choice of the alkoxide is going to be important. What else? A crossed Claisen reaction can be performed when we have two different esters, but they're only going to be useful when one of the following criteria is met. The first one is if one of the esters has no alpha protons at all, okay? So this ester here has no alpha protons, does it? Well, in that case, when you treat this ester, which does have, 1, 2, 3 alpha protons here, it's going to deprotonate, and then it's going to react with the one that has no alpha protons. Now, again, I'm really dogging on this today, but you might think, okay, well, couldn't that enolate, react with another molecule of the same ester? Yeah, I suppose it could, but it's one way to at least limit the number of products. And another way, and an even more, I'd say more widely used way, is to do a directed Claisen condensation. This follows the exact same rationale as the directed Aldol condensation, which is where we take one of the esters and we treat it with LDA. Now you've got a solution of this enolate in a reaction flask, right? And then what are you going to do? You're going to take this one here, right? And you're going to add it in here slowly. And as soon as one molecule of this touches this enolate, what's going to happen? Well, what's going to happen is that this is going to act as a nucleophile, and bang, it's going to attack here. And again, the same thing applies. Could it behave as a base, and start deprotonating it? I suppose. But again, it would be substrate specific. And in our book, we're only going to consider nucleophilic attack, all right, in order to form the Claisen condensation product. Okay, so there we go. All right, so those are the two criteria that must be met in order for a Claisen condensation to be useful. Well, we looked at an intramolecular aldol condensation reaction. What about if you do an intramolecular Claisen reaction? It's got its own name. It's named after another scientist, and it's called the Dieckmann cyclization. When I lost my job in 2007, I went to go do an interview at another company. They took me into the boss's office, and he had a chalkboard. The first thing he asked me, he said, what would happen if I took this molecule and treated it with sodium methoxide? And I said, well, I think he was just trying to make me relaxed before he asked me something, really difficult. But I said, well, I took organic chemistry as, undergraduate. I know the Dieckmann cyclization. So I said, yeah, you get this product. All right. Anyhow, the next thing he asked me was the Favorsky rearrangement, if you want to look that up. Anyhow, so the Dieckmann cyclization, it's exactly what you think it is, right? You're going to end up treating this diester. You got two esters in here. We've got acidic protons in here, don't we? We're going to pull off one of these protons with our ethoxide, right? We're going to end up ripping off one of those protons, and we're going to form an enolate. And then that enolate can do a nucleophilic attack, and we could even draw the enolate because I don't think it's in my next slides or anything. We'd end up with this enolate, wouldn't we? And then we've got a good nucleophile and a good electrophile in the same molecule, right? So we're going to end up doing a nucleophilic attack like this. And if you count the carbons, you have a 1, 2, 3, 4, 5-membered ring. All right. Like with aldol condensation reactions, Dieckmann cyclization prefers, or aldol addition or aldol condensation, sorry. Dieckmann cyclization prefers the formation of 5 and 6-membered rings. Well, with that in mind, let's try a problem. What is it here? Predict the major product obtained when each of the following compounds undergoes a Claisen condensation. Well, I'm going to try to make this one easy too, okay? And the book doesn't draw the mechanisms in gross and dirty detail. But if we're doing a Claisen condensation reaction, we would be treating this ester with sodium ethoxide, wouldn't we, in the first step? So we would get partial deprotonation, and we would end up with some of this molecule where we have some of this enolate. Okay, so now we've got this enolate and we have this ester both in the same reaction flask. And so we're going to have the enolate behave as a nucleophile, and it's going to attack here. We're going to get a nucleophilic attack, and we're going to end up losing that ethyl ethyl. And then after a couple more steps, and I'm not going to draw the whole mechanism, we can draw our final product. Let's see if we can do that. So I'm going to start by drawing this portion here. Okay, and remember, we're going to lose this OET, right? The alkoxide is the leaving group. So what's going to be attached to this carbon? Well, we're going to have the carbonyl that's reformed after the loss of leaving group, and we're going to have one carbon and then our aromatic ring, like that. So there's our final product in this case. If you want to draw the whole mechanism out, and I don't think we have to, in the amount of time that we have, if anybody wants me to draw the whole mechanism over this, it's no problem. But if you want me to do that, we'll do it on Monday. Just, mention it to me or shoot me an email and just say, hey, could you draw that for me? Draw the whole thing. And I'd be happy to do that. Okay, let's try the same thing here. We're going to treat this again with sodium ethoxide. Why? Because we have an ethyl ester, so we want to treat it with sodium ethoxide like that. So that means we're going to end up with this ester in the reaction flask, and we're going to end up with the enolate. So let's draw the enolate that would be formed, and here's the enolate. We have a good nucleophile and a good electrophile all in the same flask. Again, I'm not going to draw all of the steps out, but what you're going to end up with is something that looks like this after the loss of the leaving group. So maybe I'm going to run out of space here, and maybe I'll move this a little bit. There we go. There. All right, so what are we going to have attached to this? Well, we're going to have all of this portion of the molecule, of the second molecule left over, right? We're just going to, this guy is gone, isn't it? So what's going to be attached? Let's draw it. And all I am doing right now, okay, all I am doing is attaching this piece here onto this carbon. That's all I'm doing. So look, I'm going to draw a bond. I've got, maybe I'll draw a nicer bond. There we go. I've got a carbonyl, okay, and I've got all that other spinach. So I've got a carbon, and then I have something like this, and then I have 1, 2, and 1, 2, like that, and there's my final product. Nothing more than that. Okay, so a Claisen condensation. Again, not overly complex mechanisms, right? Just some nucleophilic attack, loss of leaving group, and proton transfers. No rearrangements, but it's being able to put the atoms together that makes these problems, sort of a end of organic chemistry 2 worthy, right? Well, let's think about some products of Claisen condensations, of crossed Claisen condensations, and think about, how would we make these? How would we make these compounds that are here, A and B? I think the easiest way to do these is to label the alpha and beta carbon to start with. Okay, here's my alpha, right? I start off with the ester. Here's my alpha. Here's my beta, like that, from the ester. The bond you're going to be breaking is this one right here. Okay, so just in terms of retrosynthesis, you're going to be starting out with this ester, ethyl propanoate, and you're going to be starting with this ester, ethyl benzoate. Those are your 2 starting materials, right? Remember, it's not an aldehyde or a ketone that you're starting with. It's a crossed Claisen. And in a Claisen, you have both reactants. Both reactants are esters. Okay? So overall, how would I put those 2 guys together in order to form this beta hydroxy ester? Well, let me write it here in a different color. Let's write it in blue. I would take my starting material, my ethyl propanoate. In the first step, I would treat that with LDA, right, to completely form the enolate. In the second step, I would treat it with the ethyl benzoate. And then, of course, in the third step, I need to have some kind of aqueous acid added, and that would give me the product. All right, so that's kind of my retrosynthetic analysis for that one. So what I want you to do before class on Monday is to, of course, read through the entire rest of the chapter if you haven't done so already, because we still have quite a bit of content to cover. It's not going to be just looking at problems, synthesis problems the whole time. I have to finish section 21.5, 21.6, and 21. So 21.6 is kind of a lengthy section. And so we got quite a bit of work to do on Monday, so be sure to read through everything ahead of time. And we'll start by taking a look at this problem here and think about the retrosynthesis here and what would our starting materials look like for this Claisen or this crossed Claisen condensation reaction.